In 4.1, we started off this chapter talking about exponential growth and decay. We did the paper folding activity and we looked at the general formula that would allow us to investigate the base to which we are raising to the unknown xth power. That base would let us know whether or not we were dealing with growth and decay. In one instance, when we were looking at applications, we talked about continuous growth or decay, and we introduced the variable, the value e. So, for example, if you look at the exponential function a of t, a function a of time, t, equaling a naught, where a with the subscript of 0 is just your initial amount you're beginning with. So a naught, a sub 0, a with a subscript of 0 is your initial amount, perhaps your initial population or your initial investment. K is the rate of growth or decay. And t is just time. Again, where k cannot equal 0, or else we're raising e to the 0th power, which is just e to the 0th power would be 1. So we'd have a constant function. Now, we talked about two situations where you can have growth, and growth is in the instance where k is greater than 0, and decay is the instance when k is less than 0. K is a negative number. And again, if we were dealing with exponential growth, where our independent variable is t, not x, and our output is a, which is a function of t, we know that our y-intercept is at 0, a naught. Because if t were equal to 0, again, that would be e to the 0th power, which would be 1, and then 1 times a naught is a naught. And we'd have exponential growth in this instance. And again, we should know that for this parent exponential function, we have a horizontal asymptote at where? At our t-axis, so that's a equals 0. If we are dealing with exponential decay in the instance where k is less than 0, again, we're dealing with t is our independent variable, a of t is our dependent variable, and then we'd have exponential decay, again, where the y-intercept or our vertical axis intercept is 0, a naught, our initial amount. And again, we'd have a horizontal asymptote at a equals 0. So those are our two situations. And again, we use this in investment problems when we are continuously compounding an investment. Now, some rules that we have become hopefully very familiar with are the instance where you have e raised to a log base e exponent, so your answer is just the argument. And similarly, if you have a power to a power, you know you need to multiply the exponents. And again, we have a to the b power. So these are different representations using our rules of exponents. Some other rules that we should recall is that ln is the shorthand for the natural log, the log base e. If you have a logarithm where the base of the logarithm equals the base of the argument, your answer, this simplifies to just the exponent. And if we saw here, we have a base raised to a logarithmic exponent with the same base, the answer is just the argument. So keeping those things in mind, we can look at some applications. So for example, if you are looking at the growth model, and here's our exponential growth model. In this case, we see that K is equal to 0.012. Since that is positive, I know it's growth. And I'm saying that this model represents Mexico's population. And it's in millions, where T is the number of years after 2006. So we said that the growth rate was 0.012. So as a percent, this would be 1.2%. If the question is how long, so at what time T, will it take Mexico to double its population? Okay, so if I have A naught equals A naught times e to the kt, and I'm looking to double the initial population, I'm looking for when the output is 2 times A naught. So in this case, I can try to solve for T, and I could then divide each side by A naught. So this is gone and this is gone. And that leaves me with 2 equals e to the kt. Now we've talked about how we need to solve exponential equations. I can take the natural log of both sides, of each side, and I'm going to take ln of 2 and ln of e to the kt. So the left-hand side is just ln of 2. Using a property of logarithms on the right-hand side, I'm left with just kt. Now, if I'm looking for the time t, when the population will double, in this case, okay, I can just keep going and solve for that time t. And I'm going to get t to equal ln of 2 over k. So this is how we would determine a doubling of the population. And that's in general. We can use that. So if we go back to this specific example and try to figure out when that time t will be of the doubling population, well, I can use this formula immediately, and I could say, well, that time will be ln of 2 divided by my k, which is 0.012. So this would be my exact time, so my exact solution. But if I wanted to find an approximation, I would put that into the calculator and I would get it to be approximately 57.76 years. So it will take approximately 57.76 years for Mexico to double its population. Now, if in the next part of the problem I'm asked how long, at what t will it take for Mexico to triple its population? Well, how do you think that we could use this general equation to solve for a time t to double its population? Well, I would modify this and I can go through the same process as I did up here, but now for tripling the population. And you should be able to get that t equals ln of 3 because we're tripling the population at a given rate. So in this case, t would be ln of 3 divided by 0.012. So this again would be the exact time, it's the exact solution, but if I wanted an approximation, t would approximately be 91.5, and this would be years. So we are saying that it will take approximately 91.5 years for Mexico to triple its population. So we can make a conjecture and we can say, how long will it take for a population to increase by a factor of n equals 2 if we're doubling, n equals 3 if we're tripling, etc. Well, t would equal ln of n over k, where n is the factor of increase. So we can make a generalization. Now you can use brute force every single time and solve this to find t, or you can kind of keep this in mind for growth. Let's look at another example. In this case, you're saying that the half-life, so we need to know what it means to have half-life. So what is half-life if you haven't learned that in chemistry yet? Half-life is the time required for an initial amount to decay to half of the original amount. That's what half-life means. So if the half-life of thorium-229 is 7,340 years, how long will it take for a sample of this substance to decay to 20% of the original amount? So I'm using A of t equals A naught times e to the kt, and I want to get my output to be the half-life, the half amount. So I'm having half the initial amount equals A naught times e to the k, and it's saying that that time for it to reach the half-life is 7,340 years. So again, I could continue to solve for the rate at which we are decaying to achieve this half-life. So I would now divide each side by A naught, and that would give me 1/2 equals e to the 7,340 k. And I need to solve for k, so I'm going to take the natural log of each side. And so that's going to give me ln of 1/2 equals 7,340 k. I'm going to divide each side by 7,340. And I'm going to get the exact rate, the exact k, is going to be ln of 1/2 over 7,000. And so that should make sense based on the previous problem, something analogous to when we were solving for t, and the approximate rate would be negative 9.44 times 10 to the negative 5th power. So in this case, I have scientific notation. Now, ultimately, I'm looking to figure out when the substance is going to decay to 20% of its original amount. So if I'm decaying to 20% of the original amount, I now am going to use, again, A of t equals A naught e to the kt, but now I have my k. I'm solving for t, and I'm trying to figure out when that's going to be 20% of the original amount. Now, I'm going to put the exact value in for k. And I'm solving for t. So in this case, again, divide each side by a naught, leaving me 0.2 equals e to this k, ln of 1/2 over 7,340 times t. I'm going to take the natural log of each side so I can get that exponent t out of the exponent. And that's going to give me ln of 1/2 over 7,340 times t. Now, if I want to solve for t, all I have to do is multiply by the reciprocal of this. So what is t going to equal? T is going to equal ln of 0.2 over ln of 1/2 over 7,340. So this is going to be ln of 0.2 times, well, when you divide by a fraction, you multiply by the reciprocal. So there is my exact time. But to get a better idea in terms of years, I would actually evaluate this on the calculator, and I'd get approximately 17,043 years. So of course I have to answer this as a complete sentence. So it will take approximately 17,043 years for a sample to decay to 20% of its original amount. So this is one type of word problem, an application of exponential equations and logarithmic equations for exponential growth and decay. Now, we should also recall that we can perform exponential regression to get an exponential model of data. So we could, as we did with linear and quadratic and other types of functions, we can enter in lists into our calculator and we can perform an exponential regression and get a curve of best fit, an exponential model that best fits data as well. So that's another application.